All right. Good evening, everyone. Thanks for joining us for this first of a series of webinars which we'll be having for people who are interested in astronomy. Just before we start, we thought we will tell you a little about what the program is. Cosmofluencer is a program which we started. It started last year as a pilot, but it's been running in its full-fledged state since October. And a small overview of what the program is so that everyone knows what it is and where we are coming from.
Humanity is rapidly moving towards establishing itself in space. We're expected to have settlements on the moon within a decade, and one on Mars by the 2040s. Exploring these frontiers is, consequently, on the top of the list of priorities for various nations and corporations around the world. India is no exception. Its Chandrayaan and Mangalyaan missions have played crucial roles in better understanding these celestial bodies. And, as a space power, India is expected to be a key player in our quest to explore the universe. Astronomy is, therefore, the science of the future. Industries linked to this field will start booming, and research and development linked to astronomy will need the smartest minds. But the smartest minds will only consider a career in this field if they are in love with it. And the prerequisite to fall in love with astronomy is understanding what it is all about. Science communicators across the world have been doing a great job over the decades in getting more and more people interested in astronomy. But while India can boast of some excellent science communicators, there is still a huge scope for many more to join in building the astronomy community in the country. Presenting Cosmofluencer, a first-of-its-kind platform for budding science communicators. The platform aims to encourage young, bright students hoping to build their future in astronomy to use their knowledge and passion to get more people to fall in love with space. 10 students, carefully handpicked after detailed interactions, will use the platform to write, create, curate and share simplified information on various topics on astronomy. These 10 science communicators, the influencers specializing on topics regarding the cosmos, are this season's Cosmofluencers.
I reside in Mumbai.
I am from Bangalore.
I am from Pune.
I am from Chittorgarh, Rajasthan.
I come from the Manipur.
I am from the Wayanad district of Kerala.
Currently, I am doing my BSc Honours degree in Physics.
I study aerospace engineering.
I am a pre-final year student majoring in electronics and communication.
I am currently in my first year of BSc Physics. I plan to use my knowledge in astronomy and data science while portraying them with the help of animations and video editing.
I see myself designing content appropriate for kids of the age group from 8 to 15.
Conducting free webinars and courses regarding astronomy.
I plan to create videos in Hindi to reach out to Hindi-speaking people across India. Thank you.
All right. So once again, thank you so much, everyone, for joining us. Like I said, this is the first in a series of conversations we are having with experts from the field of astronomy across all fields. And it is my pleasure and absolute privilege to welcome Dr. Amit Vishwas, an old friend, but more importantly, a very distinguished professor and research scientist at the Cornell Center for Astrophysics and Planetary Science. So a short word on Amit. Amit started off from Bhopal quite some time ago, a couple of decades, 3 decades ago, and he was a student at the National Institute of Technology in Karnataka, which is where he completed his bachelor's in information technology. Post that, he did his master's, and he was a passionate astro enthusiast growing up. And unlike most astro enthusiasts, he decided to follow it and made it big. He got his break when he got his master's in engineering in Cornell. Again, not directly into astronomy, but he kind of snuck his way into Cornell, which is possibly the most prestigious at least among the most prestigious universities for astrophysics. He got his M engineering in Cornell for mechanical and specializing in radio astronomy. Post which he got in as a graduate research assistant, worked in there, and finally got his doctorate there. Since then, he has worked on many interesting projects all around, many of them around radio astronomy, and I think he would love to talk about any of these projects which he's done for a long time, including the work at the observatory in Atacama, the Arecibo Observatory, and many others. So over to Amit to take you on to what he has in store for you. Thanks a lot, Amit, once again for joining us. Over to you.
Yeah, thank you, Paul. I hope you can all hear me, and I'm really happy to join all of you today. It's bright and not even, it's early and not even bright here. It's still waiting for sun to come up. So forgive me if I have some tongue twisters in there. I've tried to have my coffee early enough. Anyway, so I guess I'll start sharing my presentation and talking about it. I'll have a few questions thrown at you for a little bit. Hopefully, we can keep it interactive. And if you have any questions, please feel free to just shout out or throw them in the Q&A, and we'll make sure that we get to them. Okay. Could you please let me know when you start seeing my screen?
Yeah, it's visible.
Just need to swap my presenter view. Take this away. All right. So, hey folks, as Paul mentioned, my name is Amit Vishwas. I've been pursuing my interest in astronomy for a fairly long time. I'm very happy that I get to do it professionally. And I'm a radio astronomer by training. That basically just means that I don't necessarily take pretty pictures of the sky all the time, but I do astrophotography as a hobby on the side. And so, using much smaller telescopes or camera lenses, I do end up taking some pictures. So I'm gonna start my presentation and introduce you to the things that I'm going to be talking about today. Is my slide changing?
We're still on the first slide, Amit.
All right, how about that? All right, so I'll be starting with introducing some of the basic tools of inquiry, as astronomy is indeed a science driven by observations. In the past century, we have built increasingly sophisticated and sensitive instrumentation, and that has led to an increasing amount of discovery and scientific intrigue. To exemplify, I'll start with one of the key moments in the history of observational astronomy in the earlier 20th century that changed our understanding of the cosmos itself. I'll illustrate going on how a fundamental quantity like distance is key to measure the universe that we live in. And then we'll get to some of the interesting questions in front of us in terms of astronomy or astrophysics as a science. So the tools are simple. One is imaging. I hope most of you are pretty familiar. A camera is probably a familiar object to all of us. But remember that this was not always this tiny electronic component that we see. On the left, you see an example of one of the largest camera actually ever built. Now, what you're looking down the barrel is actually a lens, effectively. And at the back, you see a stack of CCDs, which in total sums up to about 4 gigapixels. So it's one of it is, I think, the largest camera ever built for astronomy. And it's going to be online sometime next year on conducting a survey called the Large Synoptic Survey of All Sky. That basically taking pictures of the entire sky visible to that telescope every 3 days for 3 years. So about 1,000 iterations of the same sky will help us study uh, the distribution of galaxies in the universe and also all kind of transient phenomena. And then there is spectroscopy. So that's my first question to most of you is, are you familiar with the concept of spectroscopy? And I guess we can just pop in an answer of yes or no.
Yeah, just to give you an overview, there is a poll which would show up in your console. You can answer there whether it's yes or no.
Okay. All right. So while you answer that question, I'm going to move on to the next slide and very quickly just show you some of the progress that we've had in imaging techniques. And essentially, what we started with were these plates started very early on with metal plates, moved on to glass plates, and they're treated with various light-sensitive chemicals, right? And then we figured out how to keep staring at the same patch of the sky for a while and get images of the sky and actually reveal features which were not visible to the human eye. So on the left, you're seeing one of the first images taken of the Orion Nebula. This was in late 1800s. And then very quickly, in the middle image, what you're seeing is the same patch of the sky again, slightly zoomed out. But this was an integration for of the order of an hour. So you can start seeing things that even today, if you were to look up the constellation of Orion, you won't be able to see in this image from the 1800s. And then, of course, to the to the right hand side is an image taken by JWST just a few weeks ago, and this is also showing the same patch of the sky. So I'll have the next question for all of you coming up, and the question is, could you actually see 3 of the stars that are pointed here, the image on the left, in the image on the right?
Yeah, the poll is live, so everyone can answer it. After that, we'll end it to progress.
Okay. We'll give you a few seconds to answer that, because then I'm gonna, try and squint, look at the image, maybe you'll see a pattern. All right, hopefully all of you had your attempt at that, because I'm going to reveal the answer now. And you can see those are the same 3 stars. And this interface area that you're seeing, it's called the Orion bar. And I hope most of you got that right. And this bright star that you're seeing right in the center, these spikes shining through, this is actually the star that is creating all the ionizing radiation that is creating this hole and is impinging on this bar. And there is actually star formation happening right within there. So this is a very young star, about 5 million years old. And so we've moved on from these light-sensitive chemicals in plates to solid-state detectors in the era of modern CCDs. And what we can do is really stack them up to increase the size of the field of view. So you can take pictures of bigger and bigger areas of the sky all at the same time with increasing sensitivity. So now we move on to the splitting colors part, which is spectroscopy. On the left, I have this cartoon of Newton standing at his doorway and putting a prism and splitting the sunlight into different colors. I think that you might have seen something similar in your textbooks in a while ago. So this led to one of the early discoveries of an alien element. An alien, in the sense I mean here, is something that was not detected on Earth first. All the elements that we knew of till that time were elements that were already detected on Earth. So, you guys want to hazard a guess of which element this might be? While you answer that, I'm gonna give you a little bit of how astronomers started using this tool of spectroscopy. So astronomical spectroscopy was an offshoot of chemists or alchemists back in the day, attempts to analyze materials on Earth, as well as the scientists' interest in the nature of color. What makes something red, what makes something yellow, what makes something green, so on. And what that ended up doing was giving rise to this field of astrophysics, because essentially what people figured out is that all of these signatures and colors that you see from any object actually tell you something about the constituent elements that form that object. And that, of course, led to some very early surveys in astronomical spectroscopy, starting from taking spectra of the sun because it was bright. It was obviously very important for life on Earth and to understand what life on Earth is composed of. And eventually, astronomers began to conduct large surveys of whatever stars that they could find. And two particular astronomers, Pickering and Cannon, undertook a very ambitious program of stellar spectral classification. So basically, they started taking spectra of whatever stars that they could observe, and then they started overlaying them on top of each other to match them. And by matching them, they actually started figuring out that a particular star was the same type of star as some other star in some other patch of the sky. And eventually, what this led to, of the order of about 250,000 stars were cataloged by 1924, starting from about 1890. So in a period of about 20, 30 years, 250,000 stars, the spectra was collected, analyzed, and that led to the system of 10 spectral types that we currently know of, this OBAFGKMS. Is sort of the classification for stars that we know of. And you might think that, why is this so random? It actually started with a linear order of A, B, C, D, E, F, G. And then when Annie Cannon, who was the computer at Harvard, was doing the classification of these stars, she figured out that she needed to switch things around to get the important quantity, which was the surface temperature of the star, in order. Anyway, so we ended up with this weird order of stars. All right, so quickly moving on to the next topic, which I have is island universes. And you might be wondering, what do I mean by that? Multiverses or something else? It really is a story of the tricky way through the treacherous grounds that characterize research at the frontiers of science, because we're working with information that comes with inherent uncertainties, and if we don't understand those uncertainties, how do we interpret those things? And so at the heart of this island universes debate, this was a debate that started in the earlier part of the 19th century, actually precipitated in an actual debate in 1920 that undertook. And this great debate nomenclature sort of applies to the actual running disagreement on the nature of our galaxy and the nature of spiral nebulae that ranged from the turn of the century through the 1930s till it was resolved. This debate was between many different astronomers scattered across the globe, using data and result from many instruments that took decades to resolve. And so on one side was Herbert Curtis, who was arguing about the dimension and structure of the galaxy using evidence furnished by the magnitude of the stars that he was measuring. And he argued that the spiral nebulae that you were seeing in the sky were actually separate galaxies, which were different from our Milky Way. On the other side was this young Harlow Shapley, who was also discussing the evolution of the idea of the galactic size. And he was basing his arguments on surveying the solar neighborhood and on measuring the distances of globular clusters. And he has his own ideas about the dimensions and arrangement of the galactic system. And this whole debate is an incredible glimpse into the reasoning process of eminent scientists engaged in sort of a controversy, if you may. Right? And as I was mentioning earlier, the evidence on both sides was fragmentary. So who do you think was correct? I think we'll have a question come up. And I think the options are too uncertain. Choose as best as you think you can. And I've actually laid out the arguments that both of them put on, right? So, and they were actually, quantitative arguments. Like the size of the galaxy is about 10 kiloparsecs. The other guy said that it's actually 100 kiloparsecs. One guy said that the sun was pretty close to the center of the galaxy. The other guy said that the sun is off from the center of the galaxy. And of course, the other big debate about the galaxies being external to our own Milky Way. While you answer that, you might have a good idea, given that you're here, that there are indeed several galaxies in the universe, right? So one would think that Shapley's idea of one big galaxy containing everything, and that was the universe, was perhaps flawed, right? And that was actually not the case, because as you can see, this debate lasted for decades. There were people on both sides of the argument supporting and rejecting claims. And one of the reasons behind it was back in the day when Shapley said that the Milky Way was about 100 kiloparsecs across, that number was so mind-bogglingly large that when he suggested that number, he said that that's already too big. And so imagine 100 kiloparsec number he was coming up with, and he was arguing that that was already too big. And it's not to say that Curtis himself was actually concerned about that number. And that's why what he instead did was that he made our galaxy about 10 times smaller, and then said that all these other galaxies might be out there within that 100 kiloparsec number. So what I'm showing here on the slide on the right is actually one of the imaging plates that Hubble took on 6th October 1923. And he had several of these plates that he was taking images of the same patch of the sky every day, over and over again. And so he would go back and then compare if he saw something new, or if he saw something change between an image that he took yesterday and the image that he took on this particular night. You can see several markings for N, and then one mark up here for N that's crossed out. The N typically stood for a nova, which is a type of a stellar explosion, if you may, right? But eventually, he figured out that that particular star that he crossed out from N and labeled VAR was actually a variable star. So what he found was that the brightness of that star was periodically changing. And so this was something that he'd heard about from the work of another astronomer called Henrietta Leavitt. And she had shown that the stars that are pulsating regularly, the period of their pulsation is tied to their intrinsic brightness, right? So by measuring the period of the pulsation, an observer can determine the star's intrinsic brightness. By measuring the apparent brightness of the star, what you got on the photographic plate, you can then make an estimate of how far away the star is. This is sort of, just shining a torchlight towards you. And if the person moves twice as far away, the brightness of the torchlight appears 1/4, right? And using this, Hubble deduced that the Andromeda galaxy was actually about 1 megaparsec away. So this was completely changing the idea of the size of the universe. This finding was published in 1924, and Shapley, on reading this paper, described the feeling as that it destroyed my universe. But he quickly acknowledged that his ideas about the spiral nebulae were incorrect. And quite interestingly so, after this measurement was made, because you have the scale of distance, you can actually estimate how big Andromeda galaxy was. And what they found was the Andromeda galaxy was indeed of the order of the numbers that Shapley was talking about. So while Curtis was correct about the nature of extragalactic nebulae, right, Shapley was actually correct about the size and the location of the sun in our own Milky Way. That was no small feat given the data that they were working with at that time. Now, if this was not enough, about 5 years later, Hubble actually presented something even more astonishing by plotting the velocities of the galaxies against their inferred distances. And the way that he inferred distance was not just by detecting these variable stars, but also by just simply saying that the brightest star in each galaxy must be about the same brightness. So the brightest star that we see in our own Milky Way should be about the same brightness as the brightest star that we see in some other galaxy. So he basically just went and picked stars. Now that we understood that these were actually stars and not just something that is embedded in the disk of our own galaxy, he went and picked them, measured them, and then tried to estimate that the distance to the galaxy. And then by measuring a spectral line from that galaxy, he figured out how fast was that galaxy moving. And so by plotting that, he could derive a relationship between the speed with which the galaxy was moving and its distance. And this is going to become important fairly quickly. So let's move on to the best of our knowledge. This is what the Milky Way galaxy's structure and size looks like, right? So there are spiral arms spread over a thin disk spanning over 100,000 light years. And there are globular clusters that are peppered in a spherical halo. That was deduced later, actually, by Zwicky and Rubin and their colleagues, that the velocity of the stars as you move from the center to the outer regions of the galaxy was not consistent with what you would expect based on the amount of visible matter in the region. Right? If it's matter that's keeping things bound by gravity and making things move, those stars should have been moving much faster. So more observations since then have shown similar trends on the velocity of outer stars in a myriad of galaxies, right? But that also revealed an interesting dependence on the evolutionary state of the galaxy with its morphology. So you're going to come up to the next question. What I'm showing here is sort of called this evolutionary sequence, which is the tuning fork of galactic evolution. And what Hubble and a couple other folks did with the imaging plates was he put these down and he started estimating how many stars were in these galaxies. And a fairly rudimentary way of measuring that was how bright were the centers of these galaxies. So you can measure the surface brightness of the galaxy And if you knew how far away the galaxy was, again, which he already did a few years before, figured out a way to do that, um, you could estimate the relative quantities of stars in those galaxies. So you can see ordered structures like spiral arms and central bulges, which are fairly stable. And so these all pointed to several secular evolutionary pathways, right, using these observations for a wide variety of galaxies. And these are not the only galaxies that fall on the tuning fork. This is just a particular survey that was undertaken by the Spitzer telescope in the early 2000s. So do you notice some change in the appearance of galaxies as you move from left to right? Make those observations and maybe have some questions that we can answer towards the later point of the presentation. One of the interesting things that people have understood since is that the most massive galaxies in the local universe are all elliptical galaxies that are on the left-hand part of this tuning fork. They're stripped of gas, they don't seem to be forming any new stars. And so what would be the conclusion one would make if you were to observe the most massive galaxies all look like a similar shape and size? So we'll get back to that, hopefully in terms of questions. Right. So here I show you the nomenclature for the morphology of the galaxies. There are spirals, there are ellipticals, there are irregulars. Some of them seem to have bars, some of them seem to have several spiral arms, some of them seems to have a very strong central bulge, some of them seems to have a relatively weak bulge. And so all of these things combine into presenting a coherent picture of galactic evolution. So a lot of astronomy is basically looking at pictures and trying to figure out, can we say something about a large sample based on the images that we already have? All right, so we're going to jump a few notches up and get to the point of distance, which I mentioned earlier is one of the most fundamental measurements one can make. Of course, astronomers can make. But it is also one of the most challenging measurements to make. Because remember, the scales that we are talking about are staggeringly large. Even if you look at the orbit of the Earth, it's only about 150 million miles. And we're talking about measuring distances which are tens of orders of magnitude larger, right? So to make these measurements accurately enough with, let's say, a percent accuracy of sorts, it would take a very long time. And it seems like that we're getting there. And so I'm going to walk you through how do we actually make these very sensitive distance measurements. And so what I'm showing here on the slide is the concept of stellar parallax. Now you all can do this right now. You can hold your thumb up and you can close one of your eyes or put your hand in front of your eyes and just look at, the location of your thumb with respect to something in the background, on the wall, wherever you're sitting, and then just move your hand to the other one, and you would notice that the thumb actually moves relative to the fixed things that are further far away. Now apply the exact same concept except to stars in the neighborhood, and the measurement that you're making is when Earth is in the spring side of the orbit versus the autumn side of the orbit, right? So you let 6 months elapse, and you look at the same star, and you measure its location with respect to the background stars. So this is the simple experiment parallax. In the last 5 years, a spacecraft called Gaia has really revolutionized our measurements using parallax. Initially, we were only barely able to make these measurements. In the 1980s and 1990s, there was a satellite called Hipparchus that did this. And we were only able to make these measurements in the inner part of the galaxy. Of course, there were measurements that you can make from the ground, but when you're trying to measure very small changes in positions, you need a very stable platform, and space-based platforms or telescopes typically offer you that. And so that's why Gaia has been a revolutionary mission for astronomy in terms of measuring distances. So the next rung is made up of the stars that I mentioned earlier, variable stars with change in brightness over time, and they do it periodically. So the physics that dictates these oscillations, right? It basically means that the flicker at the rate with which these the rate at which these stars are flickering is tied to their brightness, regardless of how far they are, regardless of what galaxy they're in, regardless of what neighborhood in a galaxy they are in. They might be sitting next to a black hole. They might be, sitting in a boring part of the galaxy. They might be in the center of the galaxy. They might be at the edge of the galaxy, so on and so forth. Right? And so all astronomers have to do is measure how quickly a star brightens and dims, and then calculate how bright it should be. And these variable stars are not only seen throughout our galaxy, as Hubble did in 1923. He found one in the Andromeda galaxy. And so astronomers have spotted them all around the Milky Way in different neighborhoods, and going all the way out to what's called the Virgo cluster, which is about 50 million light years away. Right? So you can measure the parallax of these stars, and you can measure the rate at which they're pulsating in their brightness. And so you get two measurements. And then in our own Milky Way, so you calibrate whatever trends you want to find out, and then you detect a Cepheid star in another galaxy. You match it with the period. You look at its period and you match it with a star in the Milky Way itself, and then you say that this is an identical star to what we are seeing in the Milky Way. So the distance to this other galaxy must be so much, because the apparent brightness of the star is lower. So that's how you make the jump from our own Milky Way to another galaxy. And this is just showing you an illustration of how the brightness of the star varies as a function of time. So with this method, you can get measurements within our galaxy and out to about 100 megaparsecs. What do we do if we want to measure things much further out? Well, you use Cepheids as far out as you can, and then you get to something that's called a type 1a supernova. As galaxies get farther and farther away, telescopes can't make out their individual stars. Right? You're fundamentally limited by how close objects can you separate using a telescope. That's called a diffraction limit. And this is sort of, if you were to see a parallel, it's the letters on an eye chart just keep getting fuzzier and fuzzier as they grow smaller, or as you take the eye chart further and further away from you, right? So your eyes can only see so far or so much and keep it sharp. So eventually, stars cannot be used as the step ladder on this cosmic distance ladder, right? So to measure the furthest galaxies, astronomers have to rely on extremely bright objects. That's how you'd be able to see them in galaxies much further out. They have to be brighter than typical stars. And one such object that's used is called a type 1a supernova. It's actually an explosion. And from what our understanding is, that these are believed to be an explosion of a white dwarf, the remnant of a sun-like star. But this explosion happens only when it surpasses a certain weight limit. Now, this is food for thought. Maybe you can tell me later, is if you know what limit am I referring to here. All right. Sorry, didn't mean to change that. All right. So now, because of the physical properties of the white dwarf, they actually cannot weigh more than about 1.4 times the mass of the sun, right? And this has been measured and observed for about 3 decades. Okay. But white dwarfs in a binary star system can eventually steal matter from their companion and accrete it onto them. And in a moment of a momentary mistake, as this matter falls onto this star, they can actually increase this limit of 1.4 times the mass of the sun. And what happens then is that the matter of that star is no longer able to hold itself gravitationally. And the entire thing basically just starts collapsing, almost like a black hole, but not just yet, right? And what ends up happening is this explosion. That's the GIF that you're seeing repeating on the screen, right? And because this explosion typically happens at relatively precisely the same mass, the amount of energy that's emitted or ejected is about the same. And so that's why you can see the same type of explosion in different galaxies and peg the distance to these galaxies based on what's the apparent brightness of this explosion. Right. Now, you have to remember, you using this step ladder to build up, going from nearby distance measures to very far away distance. We are talking about distances of the order of 10 gigaparsecs. So we are getting really far into the history of the universe itself. Okay. So if you change the precision of the very first step, the parallax measurements that you're using, then the precision of everything else changes, right? And as it happens, often enough, if you make a bad assumption in the beginning, it ends up leading to making a worse estimate on the second or the third ladder of the cosmic distance. Now I'm going to end in a couple of slides and give you a taste of cosmology. Right? So what you're seeing on your screen on the left here is the map of the cosmic microwave background. And to the best of our understanding, these exquisite observations have revealed fundamental properties of the initial conditions of our universe. So not only do they tell us about what is the current size of the universe, how did it start, it also tells you that because this field that you're seeing, this sea of red and blue, is mostly patchy, and when you analyze it, you find it that it's consistent with noise, right? So that basically means that every point on this globe is more or less the exact same conditions. And technically speaking, this map is showing you exact same temperature, right? But you're looking at a surface that existed only about 100,000 years after the Big Bang, right? So all the properties that you derive from the cosmic microwave background maps, they assume some sort of cosmology, right? So the Big Bang cosmology, the model of the Big Bang, that's sort of an assumption underlying. And the initial conditions of the universe are actually figured out by measuring the spatial scales of blobs on this map. Okay, so you're actually measuring the angle of something to figure out how far away it is. Remember, with the supernova 1, A explosions and the Cepheids and the variable stars, you were using the absolute brightness of an object as a measure of its distance. With parallaxes, again, you were using angles. So you had angles, you had brightness, angles. So this is actually the furthest surface in the universe that we can actually look. Photons cannot pass through photons from earlier cannot pass through the surface. And so whatever was behind this wall of the microwave background, we would never be able to see. So we can only infer things from before that. So what we do know now, we have absolute confidence that we live in a geometrically flat universe that has been expanding for roughly the past 13.5 billion years. And this estimate has been changing. As a matter of fact, I've probably aged by about 1 billion years between when I was in school and today, because the age of the universe changed by about that much. It used to be about 14.5 billion years, and now it's about 13.6. So I'm not an old man. So this universe has been growing in contrast to the action of gravity from what appears to be was a hot and smooth Big Bang to a very lumpy and varied universe of galaxies, stars, planets, and people that we see around, right? We are a brilliant example of overdensities. The air that surrounds us is not as dense as my hand, right? So something must have come together and led to the formation of things that are denser than other things. If you look at this map, everything should have been exactly the same, right? And these observations have forced us to accept an exotic universe of which we don't know most things about. There are these two components called the dark matter and the relatively more recently understood, well, I shouldn't say understood, we know of its existence, dark energy, right? And everything that we see around us only makes up for about 5% of the universe, right? And of that 5%, only about 0.5% makes up for everything that emits light. So that's stars. Okay. Gas also emits light, but relatively far and few. So that's why I'm not counting them. But the remaining 4.3% is actually gas, right? Hydrogen and helium makes up for most of it. Okay, so the small fraction of familiar material, most of that is not visible. It's sort of like dusting of snow on a mountain ridge, or that reveals the presence of an unseen object. One of the big surprises in the recent years have been observations that show that this rate of cosmic expansion has actually been speeding up in the last 5 to 7 billion years. And this acceleration suggests that the other 70% of the universe is composed of something called dark energy, which I've alluded to earlier. Unfortunately, we have absolutely no idea about the properties of such a dark energy. We only have a little bit, a dimly illuminated grasp that it must have some sort of a negative pressure to make cosmic expansion speed up, right? And you might ask, how do we know that this is changing, right? What you do is you take the supernova 1A explosions and you observe them at ever increasing distances, and assuming a certain type of expansion rate, if the universe was expanding faster now than it was before, the light has actually left that supernova at the time how far back you're seeing it. And so by the time that light reaches us, the effective brightness of that supernova actually drops by another factor of what's called its cosmological redshift. And we can figure those factors out by basically plugging in different models of expansion. So I'm going to sort of end with this dichotomy that we are seeing in results of the expansion rate of the universe from two different methods. On the left, you see the Planck measurements, which are completely based on the CMB scales. So you're measuring the angular scales of this last surface of scattering. And then on the green on the right, you see the mean measurement of all the measurements that are based on the cosmic distance ladder, which is parallax, takes you to variable stars, takes you out to supernova and explosions, right? And you're starting to see that the Planck measurement is completely inconsistent with the nearby measurements. And so what's changing? Right? So in this 100 years since the original great debate about the nature of the universe took place, we have observations suggesting that we live in an expanding universe and that this rate of change, of expansion, is changing. It's accelerating. How the universe is going to end, we don't know. Is there a singular model that can explain the universe in its infancy and the universe the way it's behaving today? If we believe these inconsistencies, this might actually not be true. And so you can see there are these several different methods of measuring the Hubble's constant. The funny thing is that what we are measuring is that the Hubble constant might not be constant after all, right? And you're starting to see these disagreements prop up different between different methods. Essentially, what that might be telling us is that there might be some unknown unknowns that we don't understand in the way that we are calculating distances to make measurements that are accurate down to of the order of 1%. The people who are doing this work are incredibly thorough researchers. They have certainly taken into account more things than I can even count. But this tension in the value of the Hubble constant is not fixed quickly by editing something in the standard cosmological model that we are working with right now. What that might imply is that we might have to change this cosmological model itself. But that's a big ask because the current understanding of the model, it works incredibly well. It explains all the properties of the CMB that we observe. And the one thing that sort of stands out is these cosmological tensions are not necessarily new. With the ever-changing landscape of observations and instrumentation, such tensions have indeed yielded new insights on stellar populations when it actually came to the measurement of the Hubble constant starting from the 1930s. When Hubble made the first measurement of the Hubble's constant, the number was about 500. So he made an anomalously large measurement. And what we learned there was that galaxies were moving near to the Milky Way. So there was this flow of galaxies that was understood. And once you take into account that flow of galaxies moving towards the Milky Way or away from the Milky Way, all of a sudden you find that this rate is actually relatively constant. And so all of these measurements sort of settled, as I was showing on the last slide, into the range of about 70. And then today, what we are seeing is these disagreements between 73 and 68 sort of numbers. So is there a crisis in cosmology? We'll have to wait and see the answer for that, right? And we only need more and better data so that we can understand where we might be missing some details. This might be something that will probably be solved by people in the next generation. So some of you perhaps. And so with that, I actually take you back to the very first slide that we saw. And I, on purpose, blurred the background of this image. And I'm going to take you to the actual image that it was made out of. And what you're seeing here is actually several things at play. The bright white blobs are several galaxies, which are all physically co-located. So they form a giant cluster of galaxies. As a matter of fact, the two sides of the blob are two clusters of galaxies running into each other. And what we know right now is that they've actually passed through each other at least once. And so these clusters are merging. Now, the big yellow banana sort of structures that you see there, these are actually arcs of galaxies that are in the background. And the gravitational potential of the galaxy clusters is stretching the actual shape of those galaxies and making them look like this. And the really fun thing that we've uncovered very, very recently is that in this galaxy, it's labeled 2 point something, there's a new source that popped up in 3 different places. And this is actually an image of a supernova 1A at a very high cosmological redshift. And the fact that this is happening in a lens system gives us several different ways of measuring the evolution of the Hubble's constant at that redshift. Because the rate of change of brightness of the supernova in the 3 different images actually happens slightly differently, because the light is being bent and turned towards Earth at slightly different curvatures. So there's a time delay that people can actually measure by imaging this same field over and over again and figure out what the Hubble constant should be between the background galaxy and us. And so even a single observation like this, a single source like this, can actually significantly add to our understanding of this crisis in cosmology. So with that, I'll end my presentation, and I'll be open for any and all questions that you guys have. Thank you.
Thanks a ton, Amit. I think we can go to the questions. We've got a bunch of them and we'll address all of them. There are certain generic questions as well as stuff specific to what you had, what you've presented here. So we'll start off with, I think the first question, which was asked by Arun. He says, you had mentioned about your photography. So where can we catch up on your photography? Is there any place we can catch up on?
Well, my brother's been asking me to make an Instagram account. I am not a very social media person, unfortunately. I have to think about that.
So please do share those details once you open your Instagram account. I'm sure there'll be a ton of us who want to follow it immediately.
Sure.
Right. Now, coming to this particular and the presentation, there was a question very specific to, in fact, the image which is here. The question is, the cosmic background radiation is a 2D image of the early universe. How can we assume that the universe itself is flat? Is that what we assume from this?
Yeah, so that's actually not true. You're just seeing this as a, oh yes, I can stop sharing my screen. Absolutely. You're seeing this thing projected, yes, indeed, on a 2D map. But this is, as much a 2D map as a globe is a 2D map, right? The surface of the Earth is projected in a way that you can see all of it on a flat piece of paper, or when you wrap that piece of paper around the globe. Now, the question about how can we assume the universe is flat is, we don't make that assumption. That's actually one of the parameters that you put in. The curvature of the universe is a parameter that you put in when you're measuring the cosmic microwave background, right? And the fact that the cosmic microwave background is so uniform is the bit that actually is telling us that the size of these red and blue dots is on an average pretty much exactly the same, is what's telling us that back when this thing was emitted, everything was what we refer to as was in causal contact. So whatever happened on one end of the universe knew exactly what happened on the other end of the universe, right? And that doesn't make sense in any way for what was the size of the universe at the moment when this CMB was emitted. And so the only way the CMB can be so uniform is if there was a very, very large phase of very rapid expansion. And when I say rapid in expansion, we are talking about 10 to the 30 times expanded in 10 to the minus 19 seconds or minus 31 seconds. So the universe went from a very, very tiny size to a fairly large size in a very small amount of time. And so that is what led to the curvature. Whatever was the curvature when the universe started was no longer imprinted on the CMB. And so the curvature was flattened out by the time we got to the point when the CMB was emitted. And actually, you can measure the size of these overdensities. Red is the overdensity, and blue is the underdensity. And if there was any real curvature remaining, that size would actually vary as you move to different spots of the sky. That's not the case, and that's why we infer that the curvature of the universe is flat. It's a derived quantity.
All right. So Ashfaq had a follow-up question saying, so the speed of expansion is therefore greater than the speed of light. Is that true?
That is absolutely true. Yeah. For the period of inflation. And it's not non-physical, because it is space itself that was expanding and not information that was traveling from point A to point B.
All right. Thanks, Ashfaq. Arun has another question. He says, wonderful talk. Thank you, Amit. What are you looking forward to in 2024?
Well, I actually have a very exciting thing happening personally on one of the projects that I'm working on for the past 5 years, is that instrument's getting delivered to the Green Bank telescope in mid-2024. So that's going to be sort of a 1 in 25 year kind of upgrade for the biggest radio telescope in the United States. So I'm pretty excited about what we can do with it.
Oh, that's interesting. One follow-up question on your astrophotography. Naman asks, as an astrophotographer, he himself is an astrophotographer, and he wants to know if there is, what is the gear you use?
So I've sort of thinned down the gear that I use to make sure that I can still keep doing this stuff, because oftentimes just having a lot of gear can be cumbersome. And so I have a Sony A7 III camera. At this point, I think more than 5 years old. And I have a f2.8 lens that goes from 35 to 150 millimeters. That's the one that I have been using most often. I also have a f1.8 20 millimeter lens for all the landscape photography that I do. So yeah, if you want to catch the Milky Way and you have dark skies with a f1.8 aperture, you can do that pretty easy in 10 seconds. So yeah. And in the last few years, we actually had a couple of comets pass by, which got fairly close to visible magnitude. In 2020, we had a very bright one. And that one was easy enough that I could actually just take pictures out of the window of the room that I'm sitting in.
Thanks. Thanks, Naman. One more question on the material which you had shared now. Ashfaq asks, can gravitational lensing of the galaxies lead to some error in calculating their distances from us?
Well, so gravitational lensing typically happens for sources that have cosmological redshifts, right? Because you need a galaxy or a galaxy cluster relatively nearby to you. The gravity of this galaxy or galaxy cluster is going to lens the light from another galaxy that's coming from behind. So this is a purely geometrical problem to solve. It's you can actually, if you know a little bit about optics, you can actually put this in and solve it very neatly with help of a computer, right? It is not it is a computationally intensive problem, but it's not a very difficult problem to solve. Now, the measurement of the distances of these galaxies are mostly based on cosmological redshift. They are not based on these the distance ladder that I talked about, in the sense that we don't have supernovas detected in most of the galaxies that we know of, right? a very small fraction of galaxies that we know of actually have a supernova. So what I mean by, cosmological redshift is you measure a spectral line from a galaxy, and you measure at least 2 or 3 of them, so you can make sure that you're looking at a consistent set, and you know what the rest wavelength of those spectral lines is, right? And so now, using all the observations of the supernovas, you've learned that the universe is expanding at a certain rate, okay? And then what you see is the rest wavelength, the observed wavelength of these spectral lines is actually stretched much redder as compared to the vacuum wavelength, what you would measure here on Earth. And so by dividing out the observed wavelength and the rest wavelength, you can basically measure a factor that's called 1 plus z, where z is the cosmological redshift. Accuracy for cosmological redshifts is can be very precise, because you're measuring the centroid of a spectral line, and the higher spectral resolution you have, the better measurements you can make. But for converting that to an actual distance, you're assuming a cosmological model. So you put in the amount of dark energy, you put in the amount of dark matter, and you put in the curvature of the universe, and you put in what is the Hubble's constant today, right? And so when you put all of these quantities in, and you put in the cosmological redshift, you get a number out for the distance of that galaxy. You're not directly measuring the distance to that galaxy. And of course, that number has much bigger uncertainties than the numbers that you measure with, for example, supernovas.
All right. Thanks, Ashfaq. And one final question, and this is pertinent to the last point you made. In fact, it's a question which Arun had asked even before we started this as one of the pre-webinar questions. You mentioned that you need a lot of people to solve these problems later, right? There's a lot of data coming in, and there's a lot of people you need, and possibly the next generation will solve it. So the question he asked, and I think which is there in most of our minds, is how can we motivate the next generation to look to the stars? So what do you think is going to drive interest for people to follow your path?
Well, so the one thing that I've learned about doing astronomy for however long I've been doing this is that it basically uses every single bit of technology that I can think of to make possible the next set of experiments. And the title of this talk, right, the engine of discovery, so to say, this is not a new thing, right? I am fairly sure that similar titles have been used for fields that are not astronomy. Actually, I think there's a book that's called Engines of Discovery that is written by people who work in the field of particle accelerators, right? And clearly, when you build a particle accelerator, you build enough technologies to enable that very, very difficult experiment, that those eventually seep in and make some applications available to one and all, right? One of the very good examples of particle accelerators being useful is radiation therapy, right? People who have cancer, they can actually get targeted radiation therapy done because of the advances that they've made in dealing with high energy radiation, and how you can target it, how you can precisely make sure that things go down. And so don't think of pursuing astronomy as a thing that you just do in vacuum, because I'm always looking for, particularly as a technologist, as an instrumentation, I wear the engineer hat more often than I would admit, is you have to be constantly for the lookout of what's the next thing that I can do to make my scientific experiment that much more productive, right? And that's what it comes down to, right? So when I have to code, I code. When I have to go in the lab and build a circuit, I build a circuit. When I have to sit down and run a simulation about electromagnetic fields, I do that. When I have to run the pipeline of data that's coming out from a telescope, I do that. And no one thing requires more or less attention to detail than the other. So I think at least for my path into the field of astronomy, I've certainly incredibly benefited from knowing about other things that are happening in different fields. And so to keep it exciting, what I would say is if doing new things excites you, then you can survive fairly well.
Thanks a lot, Amit. It was, I think we can wrap it up now. So thanks for this hour and 15 minutes which you spared for us. And it was an extremely informative conversation. This conversation will be on YouTube. So if anyone wants to catch up on it or share it, please do that. Amit is reachable on Twitter. He's not on Instagram yet, but on Twitter as @Vishwas. So anyone wants to follow him can do that there. And we are at Cosmofluencer on Instagram and Twitter and YouTube. So please do follow us also to keep updated on the rest of the talks which are coming in, and also just to get more information and be part of the community of astronomers in India. So thanks again. Thanks everyone for joining us, and thanks Amit for this wonderful session.
Thank you so much, and I wish you all the best for all the future endeavors.
Thank you.